Picture the very first instant of the universe, not the fire and the light you have seen in the documentaries, but the moment before all of that, the first sliver of the first second of everything. There are no stars yet because there are no atoms to build them from. There is no Earth, no sun, no galaxy turning in the dark. And here is the part almost no one stops to notice. There is nothing there to watch it. No eye, no instrument, not a single speck of dust that could record that anything was happening at all. Now hold that empty silence against a strange fact from the world of the very small, where the tiniest pieces of reality seem to stay undecided, a blur of possibilities until something takes notice and pins them down. If that is really how reality works, then who or what took notice of the universe at its first instant? And could a world like ours have become real at all, with no one there to see it? Make yourself comfortable and let your eyes close if they want to. Subscribe if you have not yet and stay with me, because tonight we follow that one question from a darkened laboratory all the way back to the morning of the world. Let's begin. Part 1. The word that doesn't mean what you think. You have never once seen an electron. You have never seen an atom with your own eyes, never watched a single particle of light leave a distant star and cross the dark to land on the back of your eye. And yet you trust the floor beneath you completely. You lie back, you let your weight go, and you assume without a second thought that the floor will hold, because the floor is made of solid stuff, and solid stuff is made of atoms, and atoms are real things sitting in real places doing real and definite things whether anyone is looking at them or not. That assumption feels like the safest one you could possibly make. Tonight, very gently, I want to take that assumption apart because the most successful theory in the history of science has been quietly telling us for 100 years that it might not be true. The trouble begins with a single word, and the word is observation. In ordinary language, observation is the thing a conscious person does when they look at something. You observe a sunset. You observe a bird at the feeder. There is a watcher, and there is a thing being watched, and the watching does not change the thing. The sunset would have happened anyway. The bird would have eaten anyway. But in the world of the very small, the word observation means something so different and so much stranger that physicists have spent a century arguing about what it actually is. In quantum mechanics, an observation is the precise moment when a system that had been behaving like a smooth spread of possibilities suddenly becomes one single fact. It is the moment the maybe turns into the is. To feel why that is a problem, you have to meet the two halves of the theory and notice that they do not fit together. The first half is an equation written down by a physicist named Erwin Schrödinger in the year 1926. The Schrödinger equation describes how a quantum system changes over time when nobody is measuring it, and it is one of the most reliable pieces of mathematics ever discovered. It has two qualities worth holding on to for the rest of tonight. The first is that it is perfectly smooth and perfectly predictable. Tell the equation what a particle is doing now, and it will tell you exactly what that particle will be doing at any moment in the future, with no gaps and no guesswork. The second quality is the unsettling one. The equation never, on its own, produces a single definite outcome. It describes a wave of possibilities that spreads out, overlaps with itself, ripples and recombines, but it never once collapses down to a single answer. Left to itself, the equation says a particle is not in one place. It is in a smear of all the places it could be, all at once. And yet, here is the second half of the theory, and the contradiction at the centre of everything. Every single time we actually measure one of these particles, we get one answer. Not a smear, not a blur of possibilities. One. The particle went through the left slit or the right slit. The atom had decayed or it had not. The needle pointed one way or the other. We have never, not once, measured a particle and found it to be genuinely in two places at the same moment. The rule that tells us the odds of each possible answer was written by another physicist, Max Born, in that same year, 1926, and the Born rule works flawlessly. Give it a wave of possibilities, and it will tell you the exact probability of each outcome you might find. But notice what the Born rule does and does not do. It tells you the odds after the fact. It does not tell you when the wave of maybes becomes the single is. It does not tell you why looking should turn a spread of possibilities into one hard fact. Between the smooth wave described by Schrödinger and the single answer delivered by every real measurement, something happens, and that something is not written anywhere in the equations of motion. There is a step in the most important theory we have that the theory itself does not describe. This gap has a name. Physicists call it the measurement problem, and I want to be clear about how serious it is, because it is easy to assume that something this basic must have been solved long ago. It has not. The measurement problem has sat at the exact centre of quantum mechanics for roughly 100 years, through every triumph the theory has had, and it is still open tonight. The recipe that most physics students are handed papers over the gap with a rule of thumb. The rule of thumb is called the Copenhagen interpretation, named for the city where Niels Bohr built his school of thought in the 1920s. The Copenhagen rule says this: until you measure it, a system obeys Schrödinger's smooth equation. At the instant of measurement, the wave of possibilities suddenly and irreversibly jumps to a single state. That jump even has a dramatic name. People call it the collapse of the wave function. And here is the part that should bother you. That collapse has never been derived from the Schrödinger equation. It cannot be. It is a second, separate rule, bolted onto the first by hand, describing a different kind of behaviour that switches on at the exact moment a measurement happens. Two different laws of motion apply to the same particle in two different situations, with a hidden seam running between them. For 90 years that seam has been handed to undergraduates as if it were settled. It is not settled. It is a wound with a bandage over it. Now we come to the word that is going to carry us all the way out to the edge of the universe tonight, so I want to define it carefully, because almost everyone gets it wrong. When physicists say a measurement or an observation collapses the wave function, they do not mean that a conscious mind has to be looking. This is the single most common misunderstanding in all of popular physics, and the people who built the theory were careful to head it off. Werner Heisenberg, one of the architects of quantum mechanics, said plainly that the observer's job is only to register a decision. He did not require an eye. He did not require a mind. He required a record. He required that the quantum event be amplified, irreversibly, into a permanent mark on the larger world. And once you put it that way, all sorts of things count as observers. A clicking detector is an observer because it leaves a record. A photographic plate is an observer because the grains of silver change and cannot change back. A single speck of dust drifting through space becomes an observer the instant a passing particle of light bounces off it in a way that can never be undone, because that collision has been written permanently into the world. An observation is a record that cannot be unwritten. Hold on to that phrase. We are going to need it later, and by the end of tonight it is going to mean something far larger than a mark on a photographic plate. So if a detector counts, and a grain of dust counts, what does not count? The answer is the one thing this whole video turns on. What does not count, in the standard reading, is nothing at all. For the wave of possibilities to become a single fact, there has to be a record. There has to be something that registers the outcome, something that gets changed in a way chance cannot erase. Take away every detector, every plate, every speck of dust, every eye, every mind. Take away everything in the universe that could possibly hold a record. And according to the theory as it is usually told, the wave does not collapse. It just keeps spreading. The maybe never becomes an is. And that should make a quiet alarm start ringing in the back of your mind, because there was a moment, a real moment, when the universe contained none of those things. No detectors, no plates, no dust, no eyes, no minds, the first fraction of the first instant of everything. And the question that Ringing Alarm is asking, the question we are going to follow patiently all the way to the end, is simply this. If a single definite reality only appears when something makes a record of it, then who or what made the first record? Who observed the universe? Let me make the double slit a little more concrete, because the part that unsettles physicists is easy to miss when it is told quickly. You can run this experiment firing the particles one at a time, with long gaps between them, so that each particle crosses the device entirely alone, with no other particle anywhere near it to interfere with. Common sense says that a lone particle, with nothing to interfere with, should simply go through one slit and make one dot, and that after thousands of lonely particles you should see two plain clumps behind the two openings. That is not what happens. Each particle does land as a single dot, yes, one at a time, like raindrops. But as the dots accumulate hour after hour, they slowly arrange themselves into the banded pattern of a wave, bright stripes and dark gaps, as though each solitary particle somehow took account of both slits on its way through and interfered with its own possibilities. A single thing, travelling alone, behaving like a wave that went two ways at once. And the only thing that switches this off is the presence of a record of which slit it used. The other detail worth holding is what physicists mean when they say the record has to be irreversible. A faint, recoverable trace is not enough. The which path information has to get tangled up with so much of the surrounding world so thoroughly that there is no practical way to gather it all back and erase it. This is why a warm, busy environment, full of jostling particles, tends to lock in definite outcomes so fast that we never see the strangeness in everyday life. The world is constantly making records of itself, everywhere, all the time, which is why your morning coffee never shimmers with quantum possibility. The strangeness is not rare because the universe is mostly classical. The strangeness is hidden because the universe is mostly watching itself. Part 2. The choice that reaches backward. Before we take this all the way out to the beginning of time, we have to sit with how strange the observer effect already is right here, in a quiet laboratory, with a single particle of light. Because if the strangeness stayed politely in the textbook, you could shrug it off. It does not stay polite. The deeper experimenters have pushed on the observer effect, the more it has refused to behave like anything our intuition is built for. And the clearest example is an experiment that the physicist John Wheeler dreamed up in the year 1978. He called it the delayed choice experiment, and once you understand it, a certain comfortable idea about time quietly stops working. Here is the setup, and I will keep it simple, because the simplicity is the whole point. You send a single particle of light, one photon, toward a device called a beam splitter, which is really just a very precise half-silvered mirror. When the photon hits it, the photon's wave of possibilities divides and travels along two separate paths at once. At the far end, you have a choice about how to finish the experiment. You can place a second beam splitter where the two paths meet again, and if you do, the two halves of the photon's wave recombine and interfere with each other, and the photon shows you a behaviour that only makes sense if it travelled both paths, like a wave, or you can leave that second beam splitter out. And if you do, you simply catch the photon at the end of one path or the other, and it behaves like a single particle that went one definite way. Wave or particle, both paths or one. And which one you see depends on whether that second beam splitter is in place. Now here is Wheeler's twist, the one that earned the experiment its name. What if you wait? What if you let the photon enter the device, let it pass the first beam splitter, let it get all the way to the point where, in any ordinary way of thinking, it has already made its choice and is already committed to being a wave on both paths or a particle on one. And only then, at the last possible instant, you decide whether to drop the second beam splitter in or leave it out. Common sense says this should change nothing about what the photon already did. The photon made its choice back at the first splitter. Your late decision can only affect what happens from here. That is what common sense says. Common sense is wrong. Imagine the room where this was finally done. Because it was done. In the year 2007, a team in Paris, led by a physicist named Vincent Jacques at the École Normale Supérieure, built exactly this experiment with single photons. They wired the final decision to a quantum random number generator, a little engine of pure chance, so that not even the experimenters knew in advance what the choice would be. The photon enters. It passes the first splitter. It is already inside the apparatus, already on its way, already, by every classical intuition, committed. And only then, microseconds later, the random number generator fires and trips a fast optical switch that decides, after the fact, whether the recombining mirror exists or not. You are in the room. You can hear the detectors at the far end registering their soft clicks. When the apparatus is closed into its wave configuration, the photons paint an interference pattern with a clarity of about 94%, the signature of something that travelled both paths. When the apparatus is left open, each detector clicks about half the time, with no interference at all, the signature of something that went one way. And the configuration was chosen after the photon had already done its travelling. Sit with what that means, slowly, because it is worth not rushing past. The choice you make now, at the end, appears to reach back and settle what the photon did earlier, at the beginning. Wheeler put it in words that are almost provocative in their plainness. He said that we decide by our choice now what the photon shall have done after it has already done its travel. And I want to be very careful here, because this is exactly the kind of sentence that gets twisted into nonsense. Wheeler was not saying you can send messages into the past. He was not talking about time travel, and nothing here lets you change yesterday. What he was saying is something quieter and, in a way, stranger. He was saying that a photon travelling through the apparatus unmeasured is simply not the kind of thing that has a definite history yet. It is not a tiny ball rolling along one definite track, waiting for you to find out which track. It is a wave of possibilities, and a wave of possibilities does not have a single past, until something makes a record that forces one. The photon does not have a story, until the universe writes it down. Until there is a record that cannot be unwritten, there is no fact of the matter about which way it went, not because we do not know, but because there is nothing there to know yet. This is the observer effect showing its true face, and notice that the conscious mind has dropped entirely out of the picture. The random number generator made the choice. No human knew the outcome until later. What mattered was not that someone looked, but that the information about the photon's path became real, became recorded, became written into the world in a way that could not be erased by chance. The moment that record exists, the photon has a definite history. Before that moment, it does not. The past itself, the path the photon took, seems to wait, unfixed and unfinished, until the present makes its choice. And if a single photon in a Paris basement can keep its history open until something records it, then a very uncomfortable question starts to take shape. One we're going to follow all the way up to the scale of everything. If the past waits on the record, then what fixes the past of the whole universe, in the one moment when there was nothing anywhere that could write a record down? Before we can reach that question honestly, we have to watch the strangeness deepen one more turn, because the next experiment does not just bend time, it makes two careful people, looking at the same world, disagree about what is real. It is worth being very clear about what the delayed choice result does not let you do, because the careful boundaries are part of what makes it trustworthy rather than magical. You cannot use this to send a message backward in time. You cannot learn tomorrow's news, or change a choice you made yesterday, or signal to the past in any way at all. When you look only at the photons arriving at the detectors, with no knowledge of which configuration was chosen, you see nothing but an ordinary, random-looking scatter of clicks. The pattern, the wave behaviour, or the particle behaviour only appears once you compare the clicks against the record of what was chosen. The information never travels the wrong way through time. Nothing arrives before it is sent. What changes instead is subtler and harder to hold, and that is exactly why it matters. The experiment does not let the present rewrite the past. It tells you that the past was never written in the first place, not in the way you assumed, until the record forced it. There is a difference between changing history and discovering that the history was not yet settled, and the delayed choice result lives entirely in that difference. The photon did not have a secret definite path that your late choice reached back and altered. The photon had no definite path at all, only a wave of possibility, and your choice was part of what finally fixed which story the universe would tell about it. That is a far stranger thing than time travel, because time travel would at least leave the idea of a fixed past intact. This does not. It quietly suggests that the past, at the smallest scale, is not a finished thing sitting behind us, but something that gets completed as records accumulate. Notice the quiet word doing the work in all of this, because it is the same word that will matter most when we reach the first instant. The word is information. What trips the change in every one of these experiments is not a conscious mind paying attention. It is information about the system becoming available to the wider world, getting written somewhere it cannot easily be unwritten. A detector that no human ever reads still counts, because the record is there. A particle of light that bounces off a single drifting speck of dust, far from any eye, still counts, because that collision has changed the speck in a way the universe now carries. The trigger is the making of a record, not the reading of one. This is worth fixing firmly in your mind because it cuts off the most common misunderstanding before it can grow, and because it makes the cosmic question so much sharper. If consciousness were the secret ingredient, you could shrug the whole thing off, since there were obviously no conscious beings at the dawn of the universe, and maybe the rules were simply different then. But consciousness is not the ingredient. The ingredient is a record, a witness in the thin, impersonal sense of something that registers an outcome and holds it. And the world today is overflowing with such witnesses, every particle of dust and gas and light constantly recording everything off everything else, which is exactly why the strangeness stays hidden from us in ordinary life. The universe now is a place of endless record keeping. The whole trouble we are walking toward, is that there was a moment when it was not, when there was nothing anywhere to make a record at all, and yet a single, definite world still came out of it. Part 3. 2 people, 1 experiment, 2 realities. We have watched a single photon keep its past open until something recorded it. Now I want to show you an experiment that takes that idea and turns it into something almost dizzying, because it does not just leave a photon's history unwritten. It lets you reach in after the fact and erase the record and watch the photon's behavior change in response to a decision you made later. This is the quantum eraser, first described by 2 physicists named Marlon Scully and Kai Drool in the year 1982 and built in a careful form by a team led by Yoon-Ho Kim in the year 1999. Picture the double slit again, the same one from the start of tonight, where a particle that goes unrecorded paints an interference pattern and a particle whose path gets recorded does not. In the quantum eraser, you set things up so that each photon, as it passes through, gets tangled together with a second photon, a partner, in such a way that the partner now carries the secret of which slit the first one took. You have made a record, and sure enough, when you check, the interference pattern is gone, because the witch path information exists somewhere in the world, even though you have not looked at it yet. Now comes the move that should not work. You take that partner photon, and before you read it, you send it through an arrangement that scrambles the witch path information beyond recovery. You erase the record, and when you now sort your original photons according to what the erased partner reveals, the interference pattern comes back. It returns in the subset where the information was destroyed, and the truly unsettling part is that you can perform the erasure after the original photon has already landed on the screen and been counted. The decision to erase or not to erase, made later, sorts the earlier events into a group that behaved like waves and a group that behaved like particles. Again, it is not about a conscious mind reading anything. It is about whether the record survives in the world. When the record exists, the photon has a definite path and no interference. When the record is erased, the path was never fixed, and the wave nature returns. The universe seems to keep its books according to which records exist, not according to who has read them. If that were the end of the strangeness, it would be enough to keep you up at night. But there is one more turn, and this one is the most disorienting of all, because it stops being about particles and starts being about people. The physicist Eugene Wigner posed it as a thought experiment in the year 1961, and it has come to be called Wigner's friend. Imagine a friend of yours sealed inside a perfectly isolated laboratory, performing a quantum measurement on a particle that is in a superposition, a smear of two possibilities. From inside the lab, your friend does the measurement and sees a definite result. For your friend, the wave collapsed. The maybe became an is. There is now a fact. But you are standing outside the sealed laboratory, and from where you stand, you have no record of what happened inside. The whole laboratory, your friend included, the particle, the instrument, and your friend's own memory of the result, are all, from your point of view, one large quantum system that no record has yet escaped. And so, applying the same physics your friend used, you must describe the entire lab, friend and all, as still being in a superposition. For your friend, there is a fact. For you, there is not yet. Same moment, same world, two honest observers, and they disagree about whether a definite reality has come into being. You might think that is just a riddle about ignorance, that surely there is really a fact and you simply do not know it yet. But in the year 2018, two physicists named Daniela Frauchiger and Renato Renner turned the riddle into something much harder to dismiss. They wrote down a careful version of the Wigner's friend setup, with more than one observer, and they proved a theorem. They showed that if you assume three things that almost everyone wants to assume, the whole structure breaks. The three assumptions are these. First, that quantum mechanics applies to everything, including observers, with no special exception for big things. Second, that when two observers each reason correctly, you are allowed to combine their conclusions without contradiction. And third, that every measurement has just one single outcome. Frauchiger and Renner proved that you cannot keep all three. Reason carefully enough with several observers inside the experiment, and they will reach conclusions that flatly contradict each other. One observer concludes the result was definitely this. Another, using the very same theory, just as carefully, concludes it was definitely not this. Picture two judges in the same courtroom, looking at the same evidence, applying the same law, each making no mistake, and arriving at opposite verdicts. Not because one of them blundered, but because the law itself, applied consistently, produces opposite verdicts when there is more than one judge. That is what they showed about the most precise theory we have ever built. Something in our picture of reality has to give. So this is where the first stretch of our journey leaves us, and I want to name the feeling honestly before we go on, because the rest of tonight depends on it. We started with a comfortable belief that things are simply real, definite, sitting in their places whether we look or not. And one experiment at a time, that belief has come loose. A photon's path stays open until a record fixes it. Erase the record, and the openness returns. Seal two observers off from each other, and they cannot even agree on whether a fact exists yet. Through all of it, one quiet question has been forming. The question that is going to carry us out past the laboratory walls and all the way to the first moment of the universe. In every one of these experiments, the thing that turns possibility into reality is a record, a witness, something that registers the outcome. So when the lights are out and the lab is empty and not one record exists anywhere, who was watching? Hold that question. We're about to meet the one physicist who refused to look away from it, and who spent the last 30 years of his life following it to a conclusion that most of his colleagues found too unsettling to repeat out loud. I want to stay with the Frauchiger and Renner result a moment longer, because it is the sharpest blade in this whole section, and it is easy to let it slide past as just another clever puzzle. The reason it matters so much is that it does not rely on anything exotic. It does not require consciousness, or hidden variables, or any controversial extra assumption. It uses only the plainest, most modest things you would want to be true of a good physical theory. That the theory works for big things as well as small. That if two careful reasoners each apply it correctly, you can trust both of their conclusions at once, and that every measurement has one definite result. Those three wishes feel almost too obvious to write down, and the theorem proves you cannot have all three together. So something on that short list, something that feels like plain common sense, is false about the world. Maybe the theory does not in fact apply all the way up to observers and laboratories, and there is some scale at which the rules quietly change, though no experiment has ever found that line. Maybe you cannot freely combine the conclusions of two observers who have measured each other, because the very act of measuring an observer does something to their recorded knowledge. Or maybe, as the many worlds people insist, measurements do not have single outcomes after all, and the appearance of one result is just the branch you happen to be riding. Each of those is a genuine sacrifice. Each gives up something you would have sworn was safe, and that is the quiet, accumulating unease of this part of the night. We started by assuming the world was simply, plainly, there. One experiment at a time, the plain version keeps turning out to be the one thing we cannot keep. Part 4. The Man Who Named the Dark. Every field has a handful of people whose names sit quietly behind the words everyone else uses, and in physics one of those names is John Archibald Wheeler. You may not know the name, but you know his words, because he is the one who gave us them. When you say black hole, you're using a phrase John Wheeler made popular. When you say wormhole, that is his word too. When physicists talk about quantum foam, the boiling uncertainty of space at the smallest scales, that is Wheeler's phrase. He was born in the year 1911, and he lived until the year 2008, and across that long life he sat at the absolute centre of 20th century physics. He had been a student of Niels Bohr, the founder of the Copenhagen School. He had been the doctoral supervisor of Richard Feynman, who had become one of the most brilliant physicists of the century. He worked alongside Albert Einstein in Einstein's final years at Princeton. This was not a man on the fringe. This was a man at the very core of the establishment, decorated, respected, central. And that is exactly what makes the last chapter of his career so hard to wave away. Because in the final 30 years of his life, John Wheeler became convinced of something that sounds, on first hearing, like mysticism, and he argued for it with the full weight of his reputation. He came to believe that observation is not a passive act that reveals a reality already sitting there. He came to believe that observation is part of what brings reality into being. He called it the participatory universe. And I want to be careful, because Wheeler was not saying that human minds have magical powers, and he spent real efforts swatting down that misreading whenever it appeared. He was saying something that follows, uncomfortably, straight from the equations we have already met. If the wave of possibilities does not become a single fact until a record is made, and if the universe is built out of these quantum systems all the way down, then the definite world we live in is, in some sense he admitted he did not fully understand, called into being by the recording of it. Not by being looked at lovingly, by being registered, by being answered. He had a way of dramatizing this that stretched the delayed choice experiment from a Paris basement all the way across the sky, and it is worth walking through slowly, because it is the bridge from the laboratory to the cosmos that the rest of tonight is built on. Imagine a single photon that left a distant quasar, one of those blazing cores of a young galaxy, 10 billion years ago. On its long way to us, the photon passes a massive galaxy sitting between us and the quasar, and the gravity of that galaxy bends the light, the way Einstein said it would, so that the photon can travel to us around the left side of the intervening galaxy, or around the right side, or, being a wave of possibilities, around both at once. The light has been travelling for 10 billion years, and tonight, here on Earth, we get to choose how to catch it. We can set up our telescope to detect which side it came around, and it will behave like a particle that took one path, or we can set it up to let the two paths interfere, and it will behave like a wave that came around both. Wheeler's point lands with full force. The same logic that let our choice in the Paris lab settle what a photon did microseconds earlier, now lets our choice tonight settle what a photon did across 10 billion years of travelling. We decide, he said, by our choice now, what the photon shall have done 10 billion years ago. The photon flying unmeasured across all that emptiness was never a tiny ball on a fixed path. It was a wave of possibility, its history unwritten, waiting for a record at the far end of time to fix what it had been. Wheeler compressed his whole vision into a single phrase in the year 1989, and the phrase is worth turning over in your hand like a stone, because it inverts everything you were taught about what the world is made of. He said, "It from bit." Every it, he meant, every particle, every field of force, even space and time themselves, derives its existence from bits, from yes or no answers to questions, from the outcomes that observation pulls out of the smooth wave of possibility. Reality, Wheeler was suggesting, is not a substance that records describe. Reality is made of the records. Think of a lone radio operator on an empty plane at night, tapping out a string of dots and dashes into the dark. At the other end, a receiver turns each dot and dash into a single bit, on or off, yes or no. There is no continuous substance flowing across the plane. There is only the message, only the bits, only the apparatus that registers them. Wheeler's claim was that the physical world is that receiver, and that what we have always called solid matter, the continuous stuff we assumed was the medium underneath everything, is at the most basic level the message itself, written in answered questions. The matter is the message, not the thing the message is about. Now I want to slow all the way down, because this is one of the moments tonight that deserves it. It would be easy to file John Wheeler under eccentric old genius and move on. It would be comfortable. But look honestly at who this was. This was not a confused man, and this was not a man chasing comfort or selling a book. This was one of the most decorated and central physicists of the 20th century, the man who named the black hole and the wormhole, a colleague of Einstein and the teacher of Feynman, and he spent the last 3 decades of his life arguing that the floor under your feet is, at the deepest level his science could reach, answered information rather than solid stuff. He did not arrive there through confusion. He arrived there by taking the equations more seriously, more literally, more bravely than his colleagues were willing to. When one of the clearest minds your species has produced follows the logic of its best theory all the way to the end, and the end is this, you're allowed to feel the floor tilt a little. You're allowed to feel how far we have already come from the safe assumption we started with. That is not a failure of nerve. That is what it feels like to look directly at what the theory says and not blink. And yet, a careful person should be suspicious here, and Wheeler would have wanted you to be. Maybe this is too much. Maybe there is a cleaner way to read the experiments, a way that lets the observer quietly drop out of the story so that the universe can go back to being made of solid stuff that does not need anyone or anything to witness it. Physicists have looked for that way out, hard, for the better part of a century. They have built several escape routes, each one an attempt to get rid of the awkward collapse, to remove the observer from the centre of the theory, and every one of those escape routes works in a sense, but every one of them charges a price somewhere else, and the prices are not small. Before we follow this question out to the beginning of the universe, we owe it to ourselves to walk through those escape routes honestly, because if one of them were free, the rest of tonight would dissolve, and the question of who watched the first instant would never need to be asked. Let me linger on the strangeness of Wheeler himself, because the temptation to file him away as an eccentric is strong, and giving in to it would be a way of avoiding what he actually saw. Consider the company he kept, and the things he built. He sat with Einstein in the last years of that towering life. He trained Richard Feynman, who would reshape physics after him. He worked on the hardest applied physics of his century. He coined the language, black hole and wormhole and quantum foam, that the entire field now speaks without thinking. This was a man at the dead centre of physical science, as rigorous and as honoured as any researcher alive, and he was not a dreamer fleeing into mysticism. He was, if anything, more literal than his colleagues. The difference was simply that he refused to look away from what the equation said about observation, where others preferred to use the equations and not ask what they meant. And where that refusal led him was to a claim that should stop you cold. Return to his radio operator on the dark plane, tapping dots and dashes that a distant receiver turns into bits, into yes and no, with no continuous substance flowing between them, only the message and the machine that registers it. Wheeler's suggestion was that the physical world is that receiver, and that the solid stuff we always assumed was the medium underneath everything is, at the lowest level, the message itself, written in answered questions. When you knock on a table and feel its hardness, you're feeling, on this reading, an enormous number of yes or no answers holding steady, a pattern of registered facts dense enough to stop your hand. That a person of his calibre, given his whole life and all his honours, chose to spend his final 3 decades arguing for this, not from confusion but from courage, is itself a kind of evidence. Not that he was right, but that the question is not the sort of thing a serious person is allowed to wave away. Part 5. No free door. Let me lay the escape routes out in front of you the way a fair guide would, one at a time, and for each one I will tell you what it buys and what it costs, because the costs are the real story. There is no free door out of the measurement problem. Every interpretation of quantum mechanics that anyone has built either keeps the observer at the centre or pays for its removal with something you may not want to give up. Walk through them with me slowly, and you will understand why the question we are chasing tonight refuses to go away. The first door is the one we have already met, the Copenhagen interpretation. What it buys you is enormous and should not be sneered at. It gives you a recipe that has worked perfectly for 90 years, that underlies every laser, every transistor, every medical scanner, every triumph of modern physics. What it cost you is honesty about that hidden seam. Copenhagen tells you the wave collapses when you measure, but it never tells you what a measurement is, or why looking should turn a smear of possibility into a single fact, or where exactly the line falls between the quantum world that spreads and the everyday world that is definite. It works, and it leaves the central mystery untouched, sitting right where the observer enters. It is a brilliant recipe wrapped around an unsolved riddle. The second door is the most famous one, and the most extravagant. It is called the Many Worlds Interpretation, and it was proposed by a graduate student named Hugh Everett in the year 1957, working, as it happens, under John Wheeler himself. Everett's move was bold. He said, "Let us simply take the Schrödinger equation at its word. The equation never collapses, so let us say nothing ever collapses. When you measure a particle that was in a superposition of 2 outcomes, you do not cause one outcome to become real. Instead, you yourself become part of the superposition. The world splits. In one branch, the particle went left, and there is a version of you who saw it go left. In another branch, it went right, and there is a version of you, just as convinced, just as real, who saw it go right. Every quantum event, everywhere, all the time, splits the universe into branches that can no longer talk to each other. What this buys you is genuine and elegant. There is no collapse, no special measurement law, no seam, and crucially, no need for an observer to single anything out, because nothing is ever singled out. Every outcome happens. But look at the price tag, because it is the largest in all of physics. To avoid one awkward postulate, you have to accept that reality is constantly branching into an unimaginable number of parallel worlds, splitting at every quantum event in every particle in every corner of space, world upon world upon world, none of which you can ever observe or visit or test. And there is a quieter cost too. If every outcome happens in some branch, then it becomes genuinely hard to say what we even mean when we say one outcome is more probable than another. Decades of clever effort have gone into rescuing ordinary probability inside the many worlds picture, and the community that believes in it has not reached agreement. So the many worlds door removes the observer, Yes, but it asks you to believe in a reality of staggering untestable size and to still explain why the odds come out the way they do. The third door keeps the world single but pays in a different currency. It is the pilot wave theory, first sketched by Louis de Broglie in the year 1927 and revived in full by the physicist David Bohm in the year 1952. The pilot wave picture says that particles are always real, always definite, always in one place, the way your intuition wants. But each particle is guided by a wave, a real wave, that tells it where to go, and the wave passes through both slits even though the particle goes through one. There is no collapse, no observer needed. Every particle has a definite position at every moment. It sounds like everything you wanted, but the bill comes due, and it is paid in something Einstein hated. The guiding wave has to be non-local. When two particles are entangled and separated by an enormous distance, the wave guiding them has to update across that whole distance instantly, so that measuring one particle here changes the guidance of the other particle there with no delay and no signal passing between them. Picture two puppets, one in New York and one in Tokyo, connected by invisible strings to a single hidden puppeteer, so that the instant one puppet lifts an arm, the other lifts its arm too, with nothing travelling between them. That is the kind of universe pilot wave theory describes, and that instant connection sits in sharp tension with Einstein's relativity, which is why the theory has never sat comfortably with the physics of particle accelerators. The pilot wave gives you back your definite particles, and charges you the orderly, separable world you thought they lived in. The fourth door tries to make the collapse real and automatic, so that no observer is ever needed. It was proposed by three physicists, Ghirardi, Rimini and Weber, in the year 1986, and a related idea was put forward by Roger Penrose, who suspected gravity itself might be the trigger. The idea is that wave functions collapse on their own, spontaneously, at random, all the time, with no measurement required. For a single particle, this happens so rarely you would wait longer than the age of the universe to see it. But an everyday object contains so many particles that, taken together, collapses are happening constantly, which is why a cat or a chair or a planet is always in one definite state. Picture a warehouse full of marbles, each one almost perfectly still, and every few 100 million years one marble on a schedule no one set suddenly twitches and settles into one exact spot. For one marble, nothing. For a wall built of 1 trillion marbles, the twitching is ceaseless, and the wall always holds one shape. This door is appealing because the collapse is real and physical and needs no watcher at all. But here is the cost. To make it work, you have to add brand new constants of nature to physics, a collapse rate and a collapse size, numbers that have never been measured, that were chosen precisely so that they sit just out of reach of our current experiments. The theory invents new machinery and tunes it to hide. To its credit, that machinery makes predictions that experiments are now beginning to test, including the gravitational version Penrose proposed, and so far no test has caught it. It is a real attempt with a real price, and the price is new, physics nobody has yet seen. The last two doors do something subtler. They keep the observer central, but they redraw what the wave function even is. One is called cubism, developed in the early 2000s, and it says the wave function was never a physical thing out in the world at all. It is a tool inside the head of the person using it, a careful bookkeeping of their own expectations, updated whenever they learn something new. On this view, collapse is not a physical event. It is just you revising your beliefs when a new fact arrives, the way you revise your guess about the weather when you look out the window. What this buys is the total disappearance of the measurement problem, because nothing physical ever collapses. What it costs is steep in its own way. Cubism declines to say that the wave function describes the world as it is in itself, independent of any mind. It hands you a calculus of expectations and goes quiet about the reality underneath. The other door, called relational quantum mechanics, proposed by the physicist Carlo Rovelli in the year 1996, says that facts themselves are not absolute. A particle has a definite property relative to the system it interacts with, and a different account can be true relative to another system, and there is simply no view from nowhere, no master list of what is really the case for everyone at once. This makes Wigner's friend stop being a paradox, because the friend's fact and your lack of one are both correct, each relative to its own interactions. What it buys is consistency. What it costs is the idea that there is one shared, absolute reality that we are all looking at. Now stand back and look at all 6 doors together, because the shape of the thing is the point. One survey after another has found that, among working physicists, no single interpretation commands even a clear majority, and fewer than 1 in 5 will firmly endorse any one of them. The field that built the most accurate theory in human history cannot agree on what the theory is telling us about reality. And notice the pattern in the prices. Each door is a different story about the same thing, the record, the moment possibility becomes fact. Copenhagen leaves the record unexplained. Many World says every record happens in some branch. Pilot wave hides the record in a non-local wave. Spontaneous collapse writes the record automatically with new machinery. Cubism puts the record inside your head. Relational mechanics makes the record relative to who is interacting. There is no door that lets you keep every comfortable intuition you walked in with tonight. Whichever one you choose, you pay in something you thought was obvious. The singleness of the world, or its separateness, or its independence from any mind, or the plain idea that there is one true story of what happened. And that quiet, genuine unease, the sense that there is no free way back to the simple solid world, is exactly what we have to carry with us now, because we're about to do the most dangerous thing you can do with a puzzle like this. We're about to make it the size of the entire universe. There is a modern refinement I owe you here, because a sharp listener will be wondering whether the whole problem has quietly been solved while we were not looking. The refinement is called decoherence, and it is real, important physics. Decoherence describes, in precise mathematical detail, how a quantum system that gets entangled with a large, messy environment very rapidly loses its ability to show interference so that it starts to look, for all practical purposes, classical and definite. It explains beautifully why we never catch a chair or a cat in an obvious superposition. The environment is constantly making those irreversible records we talked about, and decoherence is the bookkeeping of exactly how fast that happens. For a long time, some hoped decoherence would dissolve the measurement problem entirely. But look closely at what it does and does not do, because the gap it leaves is precisely our gap. Decoherence explains why the different possibilities stop interfering with each other and settle into a neat list of distinct stable options, this outcome or that one, cleanly separated. What it does not explain is why you then experience one of them rather than the others. It hands you a tidy menu and goes silent on why exactly one dish arrives at your table. The single outcome, the one definite fact out of the menu of possibilities, is still not accounted for by the smooth equation. So decoherence does not remove the observer from the story. It sharpens the question and hands it right back, dressed in better mathematics. And that is the honest shape of this entire section. A century of the finest minds, 6 serious doors, and every one of them still standing in front of the same locked room. No free door, just different prices, and the same mystery on the other side of each one. There is a feature of all these interpretations that I have been circling and should now say outright, because it explains why the argument never ends. Every one of these doors, Copenhagen and many worlds and pilot wave and spontaneous collapse and the rest, makes for almost every situation we can currently test the very same predictions. They agree on what the detectors will read, they agree on the numbers, they disagree only about what is really happening underneath the numbers, about what the world is like when no one is checking. That is why you cannot simply build an experiment to settle which one is true, the way you would settle an ordinary scientific dispute. The disagreement is not, for the most part, about what we will observe. It is about what observation even is, and what lies behind it. So this is not a case of physicists being lazy or stubborn, waiting for a clever experiment that will finally crown a winner. It is a case of a question that sits, at least for now, just past the reach of measurement, in the territory where physics shades into philosophy. The mathematics is settled and has been for 100 years. The predictions are the most accurate in the history of science. What remains unsettled is the meaning, and meaning is not the sort of thing a better detector resolves. That is the honest reason fewer than 1 in 5 physicists will plant a flag on any single interpretation. They are not confused about the physics. They are being truthful about the size of what the physics leaves open. And it is that same open territory, the gap between the flawless numbers and the unsettled reality beneath them, that widens into a chasm the moment we ask our question about the beginning, where there is no detector at all to fall back on, only the meaning exposed. Part 6. Now make it. The whole universe. Everything we have looked at so far has lived inside a laboratory, a photon, a pair of entangled particles, a sealed room with one friend inside. It is tempting to think that the strangeness is therefore small, a quirk of the tiny, something that cannot possibly matter at the scale of stars and galaxies and the great sweep of cosmic time. I want to take that comfort away from you now, gently but completely, because the observer effect does not care how big the stage is. And to scale the question up honestly, to ask who observed the universe, I first have to convince you of something that sounds like it should be philosophy, but is in fact hard-won measurement. I have to convince you that the universe had a beginning, a real one, a first moment. The case rests on 4 pillars, and they are worth knowing, because each one was a surprise, and together they are about as solid as science gets. The first pillar was laid by Edwin Hubble in the year 1929. Looking at distant galaxies, he found that they are nearly all rushing away from us, and that the farther away a galaxy is, the faster it is fleeing. Run that simple fact backward, like a film in reverse, and all the galaxies, all the matter, everything, draws together toward a single hot, dense point in the past. The universe is expanding, which means that long ago it was unimaginably smaller and hotter. That was the first hint that there was a beginning to run back to. The second pillar arrived almost by accident, and it is one of my favourite moments in the history of science, so let me put you there. The year is 1965. 2 radio astronomers, Arno Penzias and Robert Wilson, are working at Bell Laboratories in Holmdel, New Jersey, with an enormous horn-shaped antenna. They are trying to do careful radio astronomy, and they have a problem. There is a faint hiss in their instrument, a steady whisper of microwave static, and it will not go away. It comes from every direction in the sky, evenly, day and night, summer and winter. They check everything. They suspect the antenna is dirty. They find that pigeons have been roosting inside it, leaving what the 2 men politely called a white dielectric material, and they climb up and scrub the antenna clean of pigeon droppings, and the hiss is still there. Picture the 2 of them on that cold metal, out of ideas, a little annoyed, certain something is wrong with their equipment, when the truth is the opposite. Nothing is wrong with their equipment. They're hearing the cooled afterglow of the beginning of the universe, a bath of radiation left over from when the cosmos was young and hot, stretched and chilled by billions of years of expansion, down to a faint microwave whisper, the same in every direction, because it fills all of space. That whisper has a temperature of 2.72548 degrees above absolute zero, and it is the most perfect example of a certain kind of glow, a black body spectrum that has ever been measured anywhere. 2 men cleaning bird droppings out of an antenna had stumbled onto the light of creation, and for a while they did not even know what they had. The third pillar is quieter, but just as strong. Back in the year 1948, 3 physicists, George Gamow, Ralph Alpha and Robert Herman, had worked out what should have happened in the first few minutes of a hot young universe, when it was cooling through 1 billion degrees and the simplest atomic nuclei were being forged. They calculated how much hydrogen, how much helium, how much of a few other light elements should have been cooked up in those first minutes. And their prediction, made with no fudge factor, was that about 1/4 of all the ordinary matter by weight should be helium. When astronomers later measured the oldest, most pristine matter they could find, in clouds and galaxies far across the universe, they found helium making up about 24 to 25% of it, exactly as predicted. Think about what that means. 3 people, working with pencil and paper, described the universe as it was in its first 3 minutes, and the description came true in galaxies billions of light years away that no one would see for decades. That is not a lucky guess. That is a theory touching something real. The 4th pillar is the pattern of the galaxies themselves, the way they are strung across space in a faint regular web, with a characteristic spacing that shows up again and again in the great surveys of the sky, a scale of about 150 megaparsecs that was imprinted on the cosmos when it was less than 400,000 years old and has been stretched along with everything else ever since. The tiny ripples we can still read in that ancient microwave glow, variations of about 1 part in 100,000, are the seeds, and the galaxies are what those seeds grew into under gravity, and the two match. Put the 4 pillars together, the fleeing galaxies, the afterglow, the cooked-up helium, the woven pattern of the sky, and they converge on a single number for the age of the universe. 13.799 billion years. Not forever, not eternal, an age, a duration with a starting line. And here is why I walked you through all of it so carefully, instead of just asserting it. This is the same patient method, the same careful measurement that built the satellite navigation in your phone and the scanners that let a doctor see inside you without a single cut. You cannot trust that method when it is convenient and dismiss it when it unsettles you. And right now it is telling us something that should make the hair on your arm stand up, given everything we have just learned about records and observers. It is telling us there was a first instant, a morning of the world, and we're about to ask what, if anything, was there to witness it. I want to dwell on how precise these 4 pillars really are, because their precision is what turns the beginning of the universe from a story into a measurement, and a measurement is much harder to argue with. Take that afterglow, the cooled light Penzias and Wilson stumbled onto. When later satellites measured its colour in fine detail, they found it matched the ideal mathematical shape of a perfect glow, the kind a hot object gives off as it cools, more exactly than anything ever produced in a laboratory on Earth. The universe, in this one respect, is more perfect than our best instruments. That is not the kind of agreement you get from a lucky story. That is the kind of agreement you get when you're looking at something real. And the cooked-up helium is just as stubborn. When 3 physicists with pencils worked out in the year 1948 how the lightest elements should have been forged in the first 3 minutes, they were not fitting their answer to anything, because the measurements that would confirm it did not yet exist. They simply calculated what a hot young universe would do, and predicted that close to a quarter of all ordinary matter, by weight, should come out as helium. Decades later, astronomers measured the oldest, most untouched matter in distant galaxies, and found helium making up about 24 to 25% of it. The prediction and the measurement shook hands across half a century and billions of light years. When you stack all 4 pillars together, the fleeing galaxies, the perfect afterglow, the predicted helium, the woven web of the sky, they do not gently suggest a beginning. They corner you into one. And the same method that corners you is the method that runs the technology in your pocket, which is why you do not get to thank it for your maps and then disbelieve it about the morning of the world. Part 7. The beginning you cannot delete. When people first hear that the universe had a beginning, a very natural hope rises up, and it is a smart hope, the kind a good scientist should have. The hope is that the beginning is not really a beginning at all, just a moment we cannot see past yet, a curtain rather than an edge. Maybe the Big Bang was a bounce from an earlier universe. Maybe time stretches back forever, and the hot, dense moment was just one event in an endless story. If that were true, then there would be no single first instant, no morning of the world, and the uncomfortable question about who witnessed it would simply dissolve. For most of the 20th century, this hope was alive and respectable. What I have to tell you now is that One theorem at a time, the exits have been closing. The first to close them was Roger Penrose, working in the year 1965. Penrose was studying what happens when matter collapses under its own gravity, and using the mathematics of Einstein's general relativity, the same theory that has passed every test we have ever given it, he proved something remarkable. He showed that under conditions the theory itself can guarantee, a gravitational collapse does not just make a very dense lump. It runs all the way down to a singularity, a point where the curvature of space and time becomes infinite, and the equations themselves break down and stop being able to speak. Then, in the year 1970, Penrose joined with Stephen Hawking, and together they turned the same blade around to point at the universe as a whole. They proved that an expanding universe like ours, governed by general relativity and filled with ordinary matter, when you trace it backward in time, does not stretch back forever. It terminates. It runs into a singularity in the past, a moment where the classical description of space and time simply ends. The beginning was not a feature someone chose to put in the theory. It was a result the theory forced on its own authors, whether they liked it or not. But the hope was stubborn, and it had one more place to hide, and I want to be fair to it because the people who explored it were doing real and careful science. In the year 1981, a physicist named Alan Guth proposed an idea called inflation, a burst of staggeringly fast expansion in the very first sliver of a second, and inflation has since become a central part of modern cosmology because it explains a great deal. Some hoped that inflation might be eternal, that out in the larger reality, new bubble universes might be budding off forever, with no overall beginning to the whole inflating structure. The Big Bang we know would then be just the start of our bubble, not the start of everything. It was an elegant escape, and for a while it looked like it might work. Then, in the year 2003, three physicists, Arvind Borde, Alan Guth himself, and Alexander Vilenkin, published a theorem that closed even this exit. They proved that any universe which has, on average, been expanding over its history cannot be extended infinitely into the past. The mathematics is general, and it does not depend on the details of the matter or the exact theory of gravity. It says that even an eternally inflating multiverse, even a reality endlessly sprouting new bubbles, must itself have a past edge. Trace any history back far enough, and it begins. Vilenkin, who is nobody's idea of a mystic, and who was simply reporting what the equations require, summarized it with a flatness that has stayed with me. All the evidence we have, he said, says that the universe had a beginning. I want to pause here and let this land properly, because it is one of the load-bearing moments of the whole night, and it would be a mistake to hurry past it. It is easy to hear the phrase the beginning of the universe and treat it as a turn of phrase, a poetic way of talking, the kind of thing that does not quite touch the solid world. So let me make it solid. These theorems are not philosophy and they are not metaphor. They are mathematics applied to general relativity, and general relativity is not a speculation. It is the theory whose corrections keep the clocks on the satellite navigation system in your pocket from drifting. The theory that has been confirmed to absurd precision again and again for over a century. When that theory, through the work of Penrose and Hawking and the Borde-Guth-Vilenkin result, tells you there was a genuine first instant, it is telling you with the same authority that lets your phone know where you're standing. There was a real edge to time, a morning. And now hold that fact directly against everything we learned in the first half of tonight and feel the two ideas touch. The theory of the very small says a definite reality requires a record, a witness, something to register the outcome. The theory of the very large says there was a first instant, and at that first instant, by the rules of the very small, there was nothing. No detector, no photographic plate, no drifting speck of dust, no eye, no mind, nothing anywhere in existence that could hold a record of anything. The universe began in a moment when, according to our best theory of what makes things real, there was nothing present that could have made it real. You can try to soften this, and people do, and we will look honestly at every softening before the night is over, because some of them are serious and deserve respect. Maybe the standard reading of the observer effect is simply wrong or unfinished, and after another century someone will close the measurement problem in a way that needs no witness. Maybe the universe at its first instant was never really one grand wave of possibility waiting to be resolved, so that the question does not even arise. Maybe there is some way to count the universe itself as its own observer, folding back to record its own existence. Each of those is a real position, and we will weigh them. But notice that none of them is comfortable, and none of them is free, and all of them are responses to the same pressure, the same strange place where our two best theories meet and do not fit. The pressure is real. The seam we found in the laboratory, the gap between the smooth wave and the single fact, does not close when we make the system bigger. It opens wider. It opens all the way up to the size of everything, and it points at a single moment, the first one, and it asks the question we've been circling all night with a directness that is almost hard to say out loud. There was a first instant, and nothing was there to witness it, and yet a definite universe followed. So who or what was watching? Let me say a little more about why the last exit closed, the inflationary one, because it was the cleverest hiding place and the people who explored it were doing first-rate work. Inflation, that early burst of staggeringly fast expansion, was such a good idea that some hoped it might never have switched off everywhere, that out in the larger reality new bubbles of space might be budding off endlessly, with our Big Bang just the start of one bubble among countless others, and no overall beginning to the whole eternal froth. If that were true, the chain of cause and effect could stretch back forever, and there would be no first instant for anyone to have to explain. It was, for a while, a respectable refuge. What Borde, Guth and Vilenkin proved in the year 2003 is that the refuge has a flaw. They showed that any reality which has, on average across its history, been expanding cannot be stretched infinitely into the past, no matter how the matter inside it behaves, and almost regardless of the exact theory of gravity. Even the endlessly budding froth of bubble universes has to have a past edge, a point where the expanding history begins and cannot be continued backward. The phrase the mathematicians use is past incomplete, and it is a quiet phrase for a loud result. It means the road back ends. And the reason I keep returning to your phone is that this is not a fragile or exotic claim resting on untested ideas. It leans on the same general relativity whose tiny corrections keep the satellite navigation clocks above your head from drifting, the theory we have confirmed to staggering precision for over a century. When something that reliable tells you the past has a flaw, and your best theory of the small tells you that flaw had no witness on it, you are not dealing with a poetic flourish. You are dealing with two of the most tested ideas in science, meeting at a single moment and refusing to fit. I want to be scrupulously fair about who proved all this, because the conclusion is the kind that gets dragged in directions its authors never intended, and the people involved deserve to have their actual stance respected. Alexander Vilenkin, whose theorem helped close the last exit, is not arguing for any religion, and neither were the others who built these results. They are working cosmologists following their equations where the equations lead and reporting the destination without decoration. When Vilenkin wrote that all the evidence we have says the universe had a beginning, he was not making a claim about anything beyond the universe. He was stating plainly what mainstream cosmology requires, and then stopping there, exactly where a careful scientist should stop. That restraint is the model for how we should hold this all night. The beginning is a result, not a sermon. It does not, by itself, tell you what, if anything, lies on the far side of the first instant. It tells you only that the road back ends, that the past is not infinite, that there was a morning. Everything that anyone wants to say about why there was a morning, or what set it going, or whether something stood behind it, is a further step. And that further step is no longer physics in the strict sense. It is interpretation, and interpretation is where honest people part ways. So I will give you the result with full confidence, because the result is solidly established. There was a first instant. And I will hand you the meaning of that result with open hands and no insistence, because the meaning is precisely the thing the equations decline to settle. Holding those two things differently, the result firmly and the meaning loosely, is not weakness. It is what it looks like to take the science seriously without asking it to say more than it can. Part 8. Who was watching the first instant? I want to take you to the first instant now, as close as words can carry you, because you have earned the right to stand there, and because feeling it is different from being told about it. So close your eyes, if they are not already closed, and come with me to the morning of the world. There are no stars yet. Understand that there is not a single point of light anywhere, because there are no atoms to make a star from, and no space, in the ordinary sense, for a star to hang in. There is no Earth, no sun, no galaxy turning slowly in the dark, because all of that is still more than 13 billion years in the future. There is not even a second of time behind you to look back on, because time itself is just beginning, has barely begun, is thinner here than anywhere it will ever be again. And now notice the thing that matters most for our question tonight, the thing that should make the silence of this place ring in your ears. There is no detector here, there is no photographic plate, there is no instrument, no needle, no recording device of any kind. There is no speck of dust, because dust is made of atoms and the atoms do not exist yet. There is no I, there is no mind. There is, in the whole of what exists, not one single thing capable of holding a record. And if the theory we have spent all night with is read the way it is usually read, then what is here, in this first instant, is not a finished, definite universe. It is a wave function. It is a smooth ocean of pure possibility, every way the cosmos could unfold folded together at once, with nothing, anywhere, to collapse it into a single actual world. Stand in that silence for a moment, a universe of every possibility and no witness, and then, somehow, one of those possibilities became real. This one, the one with you in it, lying in the dark, listening. How? That is the participatory paradox at the scale of everything, and it is the hinge of the entire night. So let me state it as plainly as I can. In the laboratory, the wave of possibility became a single fact only when a record was made. At the first instant of the universe, there was no possibility of a record, and yet a single definite cosmos came to be, and we are living inside it. Either the rule we learned is wrong or incomplete, or something we have not accounted for did the work of the witness. And the moment you reach for that third option, the moment you say perhaps something observed the first instant, you run straight into a problem that is older than physics, a problem the ancient philosophers already knew well. Suppose you say an observer was there to make the first instant real. Then who, or what, observed that observer into being? Because if an observer needs an observer in order to be definite, then your new witness needs a witness of its own, and that one needs another, and you have started a chain running backward with no end. Either the chain goes back forever, which the theorems we just walked through say it cannot, or somewhere it has to stop at something that does not itself need to be observed into existence, something that is simply, on its own, without a record keeper standing behind it. The ancients had an image for exactly this shape of problem, and it is still the clearest one we have, so let me give it to you. Imagine a long train of railway cars sitting on a track, and not one of them has an engine. Each car is moving only because the car behind it is pushing. The first car moves because the second pushes it, the second because the third pushes it, the third because the fourth, and you can make that line of cars as long as you like, 1,000 cars, 1,000,000,000, a line of cars stretching past the horizon. But here is the thing you cannot get around, no matter how long you make the train. Unless somewhere in that line there is an engine, a car that moves without being pushed, that pushes without first being pushed itself, the entire train sits dead and silent on the rails. Nothing moves. The mere fact that the train is rolling at all is itself the proof that somewhere there is an engine, and the universe, our universe, is rolling. There is a definite world, with definite stars in definite places, and you in it. The wave of possibility at the first instant did become one actual cosmos. The train is moving. Which means, the old argument says, that somewhere at the head of the line there is an engine, something that did not need to be pushed, something that did not need to be observed in order to be real. Now I have to do the most important thing I will do all night, which is to tell you exactly where the solid ground ends. Because it would be so easy here to let my voice drop and tell you that physics has just proven what stands at the head of the chain, that the equations have handed you a name for the witness at the first instant. They have not. What physics has done is something more honest and in its way more remarkable. It has taken us by its own most reliable theories, the quantum mechanics that runs your electronics and the relativity that runs your maps, and it has marched us right up to this edge and shown us the shape of the question with a clarity no previous age could have managed. It can tell you that a definite reality seems to require a witness. It can tell you there was a first instant with no ordinary witness present. It can tell you the chain of observers cannot run backward forever. It can show you, in other words, the precise outline of the whole. What it cannot do by itself with measurement and equation alone is tell you what fills it. That is not a failure of the science. That is the science being truthful about its own border. And so here is where this beat has to leave you, holding both things at once, the pressure and the honesty. You are living inside the resolved answer to a question that our best physics can pose with perfect clarity and cannot, on its own resources, close. The universe is the record that something somehow wrote. Who was watching at the first instant when there was nothing to watch with? Keep the question. Do not let anyone, including me, hand you a cheap answer to it. Because the next move people make, when they feel this pressure, is to try to make the whole problem vanish by saying the universe simply came from nothing. And that sentence, it turns out, is doing far more quiet work than it lets on. Stay in that first instant with me one more breath, because there is a feature of the silence there that is easy to walk past and worth catching. We're used to imagining the early universe as a place, a tiny hot speck sitting somewhere, and ourselves as tiny observers who could in principle have floated nearby to watch it bang. But there was no nearby. There was no vantage point outside it from which any eye could have looked on. Whatever existed without margin, without an outside, without a seat in the audience. So the absence of a witness at the first instant is not the ordinary absence of a person who simply failed to show up. It is a far more total absence. There was no place for a witness to stand, and nothing a witness could have been made of, and no second of time in which the watching could have happened. The stage, the seats, and the lights all begin together at once with the play, and that is what makes the regress so airless when you try to escape it by adding a witness. Put an observer at the first instant to make it real, and you must ask what made that observer real, and if the answer is another observer, you must ask again. And the train of cars stretches back with no engine in sight. We met that image already. The line of railway cars each pushed by the next, dead and silent on the rails unless somewhere there is an engine that moves without being pushed. The mere fact that the train is rolling, that a definite universe exists at all with you inside it, is the proof that somewhere the chain stops at something that did not need a push. I will not tell you what that something is. The science cannot, and I promised I would not pretend otherwise. But I can tell you that the question has a shape this exact, and that the shape is not my invention. It is what you get when you take our two best theories at their word and follow them, without flinching, all the way down to the morning of the world. Part 9. The word nothing does a lot of work. You've probably heard, maybe from a popular science book or a documentary, the confident claim that modern physics has solved the old riddle, that we now understand how the universe could have come from nothing, no creator required, no mystery left. It is a thrilling sentence, and it is repeated often, and tonight I want to do something careful with it. I want to take it seriously, in its strongest form, and look closely at the single most important word in it, because that word is carrying a load it was never built to carry. The word is nothing. Several serious physicists have proposed ways the universe might have arisen on its own, and they are worth naming because these are not cranks. In the year 1973, a physicist named Edward Tryon published a short note in the journal Nature asking whether the universe might be a vacuum fluctuation. He had noticed something genuinely elegant. In general relativity, the total energy of a closed universe can add up to zero, because the positive energy locked in all the matter is balanced by the negative energy stored in gravity itself. If the books balanced to zero, Tryon suggested, then perhaps the whole universe could have popped into being as one of those tiny, fleeting fluctuations that quantum field theory says are always bubbling up out of empty space, except that this one, for whatever reason, did not vanish again. Then, in the year 1982, Alexander Vilenkin, the same physicist from the beginning theorem, sharpened the idea, using the mathematics of quantum theory to describe the universe tunneling into existence from what he called nothing. A year later, in 1983, James Hartle and Stephen Hawking proposed their famous no-boundary idea, a way of describing the universe so that asking what came before the beginning becomes like asking what is north of the North Pole, a question with no answer because the geometry simply closes off smoothly. And in the year 2012, the physicist Lawrence Krauss gathered these results into a popular book, whose title made the boldest version of the claim, presenting them as evidence that the universe could come from nothing with no need for anything more. So let us ask the simple, stubborn question: what do these physicists actually mean by the word nothing? Take Tryon's nothing first. His nothing is the quantum vacuum, the lowest energy state of the fields that fill space in modern physics. But that vacuum is not empty in the way the word suggests. It is a particular state of fields that already exist. It has structure. It has energy. It obeys the precise laws of quantum field theory, laws that are already up and running, already there. A vacuum fluctuation is a ripple in that pre-existing system, governed by rules that came from somewhere. That is not nothing. That is a very specific, very structured something, behaving according to laws nobody has yet explained the origin of. Now take Vilenkin's nothing. When you look closely at the mathematics, his nothing is a state described by an equation, a point in a space of geometric possibilities, with a quantum law telling it how to tunnel. There is an equation. There is a law of geometry. Neither the equation nor the law is itself nothing, and Hartle and Hawking's nothing is a smooth, rounded shape of space and time with no sharp edge, which is beautiful and ingenious, but a smooth shape governed by a particular rule and weighted by a particular mathematical recipe is, once again, a structured something, not the absence of all things. The philosopher David Albert, who also holds a doctorate in theoretical physics, made this point with great precision in a review he wrote of Krauss's book in the year 2012, and his point is hard to answer. The genuinely difficult question, Albert wrote, was never how matter might be coaxed out of the laws and the vacuum. The genuinely difficult question is where the laws and the vacuum came from in the first place. Every one of these proposals begins with something already in place. It begins with quantum fields, or with an equation, or with a law of how geometries are weighted. It then shows, often brilliantly, how a universe full of matter might unfold from that starting point. But it never reaches back behind the starting point. It never explains the laws themselves, or the strange fact that there is a law-governed possibility of anything at all. The old principle that out of nothing, nothing comes has not been refuted by any of them, because not one of them actually started from nothing. They started from a remarkably structured something, and called it nothing, because the something had no particles in it. And here is where this connects straight back to the thread we've been following all night, the thread about the record. Even if you grant Vilenkin is tunneling completely, even if you accept that a universe can quantum tunnel out of his mathematical starting point, look at what you get at the end of the tunnel. You do not get a finished, definite cosmos. You get a wave function. You get a quantum state, a smooth spread of possibility, the very thing that, by everything we have learned tonight, still needs something to make it into a single actual world. The nothing these theories begin with already contains a law, a structure, a kind of pre-written record of what is allowed, and the something they end with is a wave still waiting to be observed. The dramatic claim, examined slowly and without heat, quietly deflates into honesty. Physics has shown us, in gorgeous detail, how a universe might grow from a particular structured beginning. It has not shown us a universe growing from genuine nothing, and it has not removed the need for a witness. It has only pushed both mysteries one step further back and hoped we would not follow. And once you have seen that, a new question rises, because if there really was a structured beginning, a specific starting state with specific laws and specific settings, then you are allowed to ask how specific. You are allowed to ask how finely that first state had to be arranged for any of this, for galaxies, for stars, for carbon, for chemistry, for a listener in the dark, to be possible at all. And when you ask that question and go looking for the answer, you find a number. It is the most improbable number in all of physics, and it is so far beyond ordinary language that no tongue on earth has a word for it. I told you near the start of tonight that we would come back to a number with no name. We are ready for it now. There is one more piece of Trion's idea worth turning over, because it is genuinely beautiful, and it is also where the sleight of hand hides. Tryon noticed that the books of a closed universe can balance to zero, the positive energy of all the matter exactly cancelled by the negative energy stored in gravity, so that the grand total comes out to nothing at all. From that, he reasoned, perhaps the whole universe could have flickered into being for free, the way tiny fleeting fluctuations are always flickering up out of empty space and vanishing again, except that this one did not vanish. It is an elegant thought, and it has a real insight in it. But notice the floor it stands on. Those fleeting fluctuations happen in a quantum vacuum, and a quantum vacuum is not the absence of everything. It is a busy, structured state of fields that already exist, obeying laws that are already in force. For the books to balance to zero, there already has to be a system with books to balance. This is the point the philosopher David Albert pressed so cleanly, and it is the hinge of the whole section. The genuinely hard question was never how matter might be drawn out of the laws in the vacuum, because clever physics can often manage that. The genuinely hard question is where the laws in the vacuum came from in the first place, and not one of these proposals so much as touches it. They all begin with a remarkably specific something, a field, an equation, a rule for weighting geometries, and they call it nothing because it happens to contain no particles. Then they show how particles and space and time can grow from it, and the popular version of the story drops the fine print and announces that the universe came from nothing after all. And even granting every step of the mathematics, look again at what you are handed at the end of the tunnel. Not a finished, definite cosmos, but a wave function, a smooth spread of possibility, the very thing that still needs something to make it one actual world. The word nothing was doing the heavy lifting the whole time, and it was never nothing. It is only fair to dwell for a moment on how genuinely lovely some of these origin ideas are, because dismantling the word nothing should not become a way of sneering at the physics, which is first-rate. Take the no-boundary proposal that James Hartle and Stephen Hawking put forward in the year 1983. Their idea was that if you handle time in a certain careful mathematical way near the very beginning, the universe has no sharp starting edge at all, but instead rounds off smoothly, the way the surface of a globe rounds off at the pole. On this picture, asking what came before the beginning becomes like asking what lies north of the North Pole, a question that sounds fine but points at nothing, because you have run out of north. There is no earlier moment to find, not because something is hidden, but because the geometry simply closes. That is a beautiful and serious piece of work, and I do not want to wave it away. But hold it up to the light and look at what it is made of. A smooth rounding off of space and time is still a particular shape, governed by a particular rule, weighted by a particular mathematical recipe for how likely each shape is. The pole of a globe is not nothing, it is a very specific geometry. So even here, in one of the most elegant origin stories physics has produced, The starting point is a structured something, an equation, and a geometry and a rule, not the genuine absence of all things. The proposal removes the sharp edge of the beginning, which is a real achievement, but it does not, and does not claim to, explain why there is a law-shaped possibility of any geometry at all. The hard question, David Albert pointed to, survives every one of these elegant moves intact. Where did the laws, the rule, the very space of possibilities come from? None of the answers reach behind themselves to touch that. Part 10. The number with no name. Let me build up to the number carefully, because if I just said it out loud first, you would not feel it, and this is a number that has to be felt rather than heard. Start with the gentler version of the mystery, the one physicists call fine-tuning. Our universe runs on a couple dozen basic settings: the strengths of the forces, the masses of the fundamental particles, the amount of energy in empty space, and so on. And what physicists have slowly realized, sometimes to their discomfort, is that these settings appear to be balanced on a knife's edge. Nudge them, even slightly, and you do not get a different, interesting universe. You get a dead one. As an example, consider the strong nuclear force, the force that binds atomic nuclei together. There is a delicate coincidence inside stars that lets 3 helium nuclei come together to form carbon, and that coincidence depends on the strong force having very nearly the value it has. Change that force by a few percent in either direction, and the carbon-making step in the hearts of stars fails, and a universe without carbon is a universe without carbon chemistry, which means without biology, without you. Or consider the tiny difference in mass between the neutron and the proton. Shift it by a small amount one way, and the universe ends up as nothing but hydrogen. Shift it the other way, and you lose hydrogen entirely. And either way, the chemistry that makes life possible never gets started. The astronomer Martin Rees wrote a book in the year 1999 called Just 6 Numbers, in which he showed that 6 of these settings each had to fall inside a narrow life-permitting window, and he was not arguing for any conclusion beyond the mathematics. The mathematics is simply what it is. There is one setting that has caused physicists more pain than all the others, and it sets us up for the number with no name. It is the energy of empty space, the cosmological constant. We can measure its value, and it is very small but not zero. The trouble is that when you ask quantum field theory, our best theory of the very small, to predict that value from first principles, it does not miss by a little. It overshoots by a factor of 10 followed by 120 zeros. That gap, 120 orders of magnitude, is the largest disagreement between a theoretical prediction and a measured value anywhere in the history of science. People sometimes call it the worst prediction in physics. Whatever process actually sets the energy of empty space has, in effect, cancelled the naive prediction down to 1 part in 10 followed by 120 zeros, leaving just the faint whisper we observe. If it had not, there would be no galaxies, no stars, no structure of any kind, just a universe blown apart or crushed shut before anything could form. And now we are ready. Because Roger Penrose asked a related but even more staggering question, and got an even more staggering answer. Penrose wanted to know how special the very beginning of the universe had to be, not in its forces or its particle masses, but in its order, its tidiness, what physicists call its low entropy. The early universe had to start in an extraordinarily orderly low entropy state, because the whole long story of the cosmos since then, the forming of galaxies, the lighting of stars, the unfolding of time itself, has been a slow slide from that orderly beginning toward greater and greater disorder. Penrose compared the orderliness of the actual beginning to all the ways the same matter and energy could have been arranged, and he asked how improbable that orderly start was if you imagine it chosen by blind chance. The answer he reached is the number with no name. The chance he estimated was about 1 part in 10 to the power of 10 to the power of 123. I need you to understand what that stack of words means, because it is not an ordinary large number. It is not a 1 followed by 123 zeros, which would already be unthinkably huge. It is a 1 followed by 10 to the power of 123 zeros. To simply write the number out in full, you would need more zeros than there are particles in the entire observable universe. You could not fit the number into the cosmos it describes. There is no name for it, in any language, because no human language ever needed one. I want to slow all the way down here, because this is the second to last place tonight where I am going to ask you to feel something, rather than just follow it. And it is the place where this number stops being a curiosity and becomes personal. Why should you, lying in the dark, care about Penrose's impossible number? Here is why. That fantastically improbable, fantastically orderly beginning is the only reason your life has a shape at all. The fact that you can remember this morning but not tomorrow, the fact that a cup of tea cools in the room and never spontaneously heats back up, the fact that there is a direction to time, a before and an after, a past you can recall and a future you cannot. All of it rests entirely on the universe having begun in that absurdly orderly, absurdly improbable state. The arrow of time, the thing that makes your life a story instead of a smear, the thing that lets a moment mean something because it will not come again, is a direct inheritance from that first instant, the one with no witness, the one settled to a precision the universe itself is too small to write down. You are living along that arrow right now, in this very moment of listening, because the morning of the world was tuned to a sharpness that has no name, and that orderly, unwitnessed, impossibly precise beginning is the same beginning we said no detector recorded, the same wave function we said had nothing to collapse it. The number with no name is not separate from the question of who was watching. It is the question, written in the one language the universe does speak, which is mathematics. How did a first instant with no observer come to be set with a precision that beggars all description? People have answers. We owe it to ourselves to hear the honest ones and to see exactly how far each of them can actually carry us. Let me try one more way of feeling the size of Penrose's number, because numbers this large stop meaning anything unless you fight to keep them concrete. Picture the most ordinary kind of unlikely thing, shuffling a deck of cards and having it come out in perfect order, every suit sorted, every rank in line. That is improbable, about one chance in many billions of billions, but it is the kind of improbable a patient universe could stumble into if it shuffled enough decks. Now imagine that outcome, a perfectly sorted deck, repeated not once but for a separate deck, at every star in every galaxy, and then that whole staggering result multiplied by itself again and again. In a tower of multiplications you would have to keep writing past the edge of the observable universe. You're still not close to Penrose's number. The orderliness of the first instant was less probable by blind chance than all of that. It is not a large number in the ordinary sense. It is a number that breaks the ordinary sense of large. And I keep insisting that you feel it, rather than just hear it, because of what it is actually measuring. It is measuring how finely the beginning had to be set for time itself to have a direction. The reason you can hold a memory of your childhood, but not of next week, the reason a shattered glass never gathers itself back onto the table, the reason your life runs one way and means something because it does, all of it traces straight back to the universe having started in that absurdly orderly, absurdly improbable condition. The arrow of time is not a small bookkeeping detail. It is the thing that makes experience possible at all, and it is a direct inheritance from the unwitnessed first instant, the one set to a sharpness with no name. Every moment you live through, including this one, is you riding that arrow outward from a beginning tuned more finely than the cosmos has room to write down. The number with no name is not a fact about the distant past. It is the reason your night has a tomorrow. Part 11. The Interpretations of the Beginning. So here we are, at the place where honest people disagree, and I am going to try to be the fairest guide I can be, because this is exactly the kind of question where it is easy to push too hard in one direction and lose your trustworthiness. We have a definite universe that, by our best theory of the small, seems to need a witness, and a first instant that, by our best theory of the large, had none, set to a precision that has no name, The question is what to make of that. And there are several serious answers, and I owe you the strongest form of each, including the strongest form of the one that points somewhere unsettling. Let me give you that unsettling one first, in its most rigorous dress, because it deserves to be heard clearly rather than caricatured. Some thinkers look at this whole picture and conclude that the witness at the first instant and the cause of the beginning must lie outside the physical universe entirely, because the universe is the very thing being explained. The reasoning runs along two tracks that arrive at the same station. The first track is the one we have followed all night, John Wheeler's participatory line, which notes that a definite reality seems to require observation, and that the cosmic reality became definite when no ordinary observer existed. The second track is much older. It is a classic argument that the medieval philosopher Al-Ghazali set down in the 11th century, and that the philosopher William Lane Craig revived and sharpened in the year 1979. It goes in three short steps. Whatever begins to exist has a cause. The universe began to exist. Therefore the universe has a cause. And that cause, the argument continues, cannot itself be part of the universe, since the universe is what is being caused. So it must stand outside space, outside time, outside matter and energy, not bound by the laws it grounds. The two tracks, the observer at the first instant and the cause of the beginning, point at the same kind of thing, something prior to and independent of the physical world. There is even a remarkable biographical data point that people in this camp like to cite. The philosopher Antony Flew, who for 50 years had been the most prominent academic defender of atheism in the English-speaking world, announced in the year 2004 that he had changed his mind and come to accept a kind of creator, pointing to the fine-tuning of the constants and the difficulty of explaining life's origin by unguided processes as the things that moved him. He did not adopt any particular religion. He simply concluded that the most economical reading of the evidence required a mind behind the universe. Now I am going to do the thing that keeps this channel honest, which is to give the other side exactly as much room and exactly as much respect, because this argument, powerful as it feels at this hour of the night, is one interpretation among several, and it is not where the science ends. It is where the science hands off to philosophy. Here are the serious replies, and you should weigh them with real care. First, remember the survey. Among the physicists who have spent their lives inside this theory, no single interpretation commands a majority, and fewer than 1 in 5 will firmly endorse any one reading. The field is genuinely unsettled, which means nobody in any direction gets to claim the matter is closed. Second, the leading physics alternatives do not require any mind at all. The many worlds interpretation, which we met earlier, removes collapse completely, so that nothing ever needs a witness, because every possibility simply happens in some branch, and on that view, the cosmic wave function never needed observing into definiteness in the first place. Relational quantum mechanics goes further and denies that there are absolute observer-independent facts at all, which does not answer the question who observed the universe so much as dissolve it, by saying the question assumes a kind of fact that does not exist. Third, the fine-tuning has a famous naturalistic candidate, the multiverse. If there are enormously many universes, each with its settings shuffled differently, then a few will land in the narrow life-permitting window by sheer chance, and we, being alive, could only ever find ourselves in one of those few. The multiverse is a serious idea, but notice, in fairness, that it does not get something for nothing either. Whatever machinery generates all those universes with all those different settings is itself a structured, law-governed thing, and so it inherits the very question it was meant to answer. What made the universe generator and set its rules? The chain does not vanish, it just moves up one floor. There is a sharper reply too, made by thoughtful physicists like Sean Carroll, and I want to give it its due because it strikes at the root. Carroll argues that the demand for a cause of the universe may be a kind of category error. Causation, he points out, is a relationship we observe between earlier events and later events, inside time. But the first moment of time has no earlier moment, so asking what caused the first moment may be like asking what lies north of the North Pole, a grammatically fine question that does not actually pick out anything. On this view, the universe just is, at its first instant, the brute starting point of all the causation there is, and the request for a further cause is malformed. It is a powerful move. But notice, and this is the honest part, that this reply is itself a piece of philosophy, not a measurement. Whether causation must be confined to relations within time is exactly the kind of question that cannot be settled with a telescope or a particle detector. So Carol is allowed to make that move, and the person who finds it unsatisfying is allowed to resist it, and what you are watching, when those two argue, is not science against superstition. It is two metaphysical pictures, neither of which the equations can referee. That is precisely why the question stays open. One more idea belongs here, because it is everywhere in the culture, and it turns out to be closer to our theme than it first appears. It is the simulation hypothesis, the suggestion, given a careful form by the philosopher Nick Bostrom in the year 2003, that we might be living inside a computer simulation run by some advanced civilization. Set aside whether you find it likely, and notice only what it does to our question. If reality is generated by a computation running in some base world, then you have not removed the need for a mind-like ground of things. You have moved it. The base reality that runs the simulation is itself a structured, law-governed world, inhabited by minds clever enough to build universes, and so the very same questions, why is there a structured reality at all? What grounds it? What began it? Simply reappear one level down. The simulation idea does not escape the participatory question. It restates it, with the witness relocated to a programmer, and leaves the deeper mystery of the base world exactly where it was. And so, having walked through all of it fairly, here is the disciplined truth, the one I will not dress up in either direction. The most rigorous version of tonight's question really does press towards something outside the physical universe, a ground that is not itself another structured contingent thing, and physics, by itself, with measurement and equation alone, cannot tell you what that ground is, or whether to call it a mind, or a law, or a brute fact, or by any older name. It can pose the question with startling clarity. It cannot certify the answer. Anyone who tells you the equations have proven a creator is overreaching, and anyone who tells you the equations have closed the question is overreaching too. The honest place to stand is in the open question itself, and that is exactly where I want to leave you as we come, gently, to the end. I want to add a little more weight to the fair side of this, because it would be easy, at this hour and on this subject, to let the unsettling reading quietly win just by sounding profound, and that would not be honest. So consider the multiverse answer to the fine-tuning once more, carefully, because it is the favourite naturalistic reply, and it deserves its best form. The idea is that if reality contains an enormous number of universes, each with its dial set differently, then a small fraction will happen to land in the narrow window that permits stars and carbon and chemistry and life, and we, being alive, could not possibly find ourselves anywhere except in one of those rare friendly ones. On its own terms, that works. It really would explain why we observe finely tuned numbers without anyone having tuned them. But notice the cost, in fairness, that it does not advertise. Whatever generates that ocean of universes with their shuffled settings is itself a structured, law-governed mechanism with its own rules and its own settings. And so the question you asked about our universe simply reappears about the universe maker. What set its rules? The explanation does not dissolve the mystery. It relocates it one floor up and hopes you will not climb the stairs. And then there is the cleanest reply of all, the one that says the question itself is malformed, that asking for a cause of the first moment is like asking what lies north of the North Pole. I gave that reply its due already, and I want to honour it again, because it is genuinely powerful. But hold on to the honest detail. whether causation must be confined to relations inside time is not something you can settle with a telescope or a collider. It is a claim about the deepest grammar of explanation, and reasonable people pull in opposite directions on it. So when a careful physicist says the question is malformed, and a careful philosopher says the question is forced, you're not watching knowledge defeat superstition. You're watching two ways of thinking about explanation itself, neither of which the equations can referee. That standoff is not a temporary gap that better data will close. It is the actual edge of what physics, as physics, is able to say. And standing honestly at that edge, refusing to fake a measurement we do not have, is the most rigorous thing we can do. Let me also restate, because fairness demands the repetition, that the leading physics on offer does not actually need anything outside the universe, and a careful listener should keep that firmly in view against the pull of the late hour. The many worlds interpretation, taken seriously, removes collapse entirely, so the cosmic wave of possibility never needed witnessing into a single reality, because on that view, every possibility simply happens, each in its own branch, and the appearance of one definite world is just the branch we ride. If that is right, the whole participatory puzzle never gets off the ground. And relational quantum mechanics goes another way to the same relief, by denying that there are absolute observer-independent facts at all, so that the demand for someone to have observed the universe into a single objective state rests on a kind of fact the theory says does not exist. Neither of these is a fringe dodge. Both are positions held by serious physicists, and both make the unsettling reading unnecessary. So weigh it honestly, the way you would weigh anything that matters. On one side, a genuinely rigorous line of reasoning that presses toward a ground outside the physical world, taken seriously by real thinkers and reached, in his own way, by a man as central as John Wheeler. On the other, serious physics that needs no such ground, a multiverse that explains the fine-tuning at the price of its own unexplained machinery, and a careful argument that the whole demand for a cause of the beginning may be malformed. No single view commands the field. The equations referee none of it. What you're left with is not an answer handed down by science, but a question held open by it, more sharply than any age before us could hold it. And there is a strange dignity in that, in being the first people able to state the mystery this precisely, and honest enough not to fill the silence with a certainty we have not earned. Part 12. Can reality exist on its own? Let me draw the two halves of tonight together now, slowly, the way you would pull a blanket up at the end of a long day. We began in a laboratory with the strangest word in physics, the word observation, and we found that a definite reality seems to come into being only when a record is made, a mark that cannot be unwritten. We watched that idea refuse to stay small. We watched a choice reach back and settle a photon's past, watched an erased record bring a vanished pattern back, watched two careful observers fail to agree on whether a fact even existed yet. We met the man who named the dark and followed that idea to its end, and we found that the way out through the many doors of interpretation always charged a price, and never a small one. Then we did the dangerous thing. We made the question the size of the universe. We found, by the same patient measurement that runs your phone and your maps, that there was a first instant, a morning of the world, and that at that morning there was nothing, anywhere, that could hold a record. We found that the claim of a universe from nothing quietly smuggles in a structured something every time. And we found, at the beginning, a precision with no name, the orderliness that gave you the very arrow of time you're riding right now. Put it all in one sentence and feel the weight of it. Our best theory of the small says reality may need a witness in order to be definite, and our best theory of the large says there was a first instant when no witness existed, and a definite universe came to be anyway, tuned to a sharpness beyond all language. That is not a proof of anything. I have been careful all night not to let it become one. It is something stranger and I think more honest than a proof. It is a genuine open question, sitting at the meeting point of our two greatest theories that we do not get to close by waving a hand in either direction. Maybe our century-old reading of the observer effect is simply unfinished, and one day someone will show how definiteness arises with no witness needed, and the whole pressure will quietly release. Maybe the cosmos at its first instant was never truly one grand wave awaiting resolution, and the question rests on a picture we will outgrow. Or maybe reality really is the kind of thing that has to be witnessed to be definite, and grounded by something to begin, and we are living, every second, inside the standing answer to a question we can pose and cannot finish. All three of those remain live. Honesty means holding them all and refusing to pretend the discomfort away. So let me bring you, one last time, all the way back from the morning of the world to right here, to where you actually are. You're lying in the dark, eyes closed, the sound of my voice the only thing in the room, and every solid thing around you, the floor that holds you, the walls, the air, your own resting hands, is made, at the bottom, of those same quantum systems whose definiteness our best theory cannot fully account for on its own. On the most literal reading of the physics, every one of those things is holding its definite reality moment to moment, and the question of what sustains that holding, whether reality can keep itself, or whether being definite is something quietly conferred, is the same question we carried out to the first instant and back, and it is no nearer to a tidy answer now than when we began. That is not a thought meant to frighten you, though it has an edge of unease in it, and I will not pretend it does not. It is meant to leave you with the right kind of wonder, the kind that comes from standing at a real border of human knowledge and seeing, clearly, how much is still unwritten. The universe is the record that something, somehow, wrote, and we still do not know what held the pen. Who was watching, at the first instant, when there was nothing to watch with? The honest answer, the one I will not cheapen for you tonight, is that nobody knows. And so I will leave you where the science actually leaves us, inside the question itself, turning it over gently as you drift, the oldest question wearing its newest clothes. Can reality exist on its own? Sleep well, if you can, inside a universe that has not yet told us whether it needs to be seen. Before I let you go, let me hand the three open paths back to you one more time, gently, so you can carry whichever one you like into the dark, because the honest gift of tonight is that the choice really is still yours to weigh. The first path says our 100-year-old reading of the observer effect is simply unfinished, and that some future insight will show how a definite reality can arise with no witness at all, releasing the whole pressure we have been feeling, and that would be a magnificent thing to live to see. The second path says the universe at its first instant was never truly one grand wave awaiting resolution, that we have been mispicturing the beginning, and that the question quietly dissolves once we learn to see it rightly. And the third path says reality really is the kind of thing that must be witnessed to be definite and grounded to begin, and that we are living, every second, inside the standing answer to a question we can pose with perfect clarity and cannot from inside ever finish. I have been careful not to choose for you because the science does not choose, and I would rather leave you honest than leave you certain. So here, at the end, is the only thing I will say plainly. Reach out, in the dark, and touch whatever is nearest you, the edge of the bed, the wall, your own hand. It is steady. It is definite. It is simply, reliably there. And the most successful theory humans have ever built cannot fully tell you why it gets to be that way on its own, or whether on its own is even the right phrase. The universe is the record that something somehow wrote, and we still do not know what held the pen, who was watching at the first instant when there was nothing to watch with. Nobody knows, and I will not pretend for you that they do. Let that be a soft thing tonight rather than a sharp one. You're a small, warm, definite fact in a cosmos that does not yet add up, lying safe inside a mystery far older and far larger than you, allowed, for one night, simply to wonder at it. Can reality exist on its own? Rest now, and let the question keep its own watch until morning.